Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square ABCD. One side of this square equals to 8 units. So AB equals to BC equals to DC equals to AD equals to 8 units. And inside square ABCD we have two circles. The radius of this big circle equals to 2r, and the radius of this small circle equals to r, and we want to find out the value of r, the radius of this small circle, or the size of the radius of this small circle. Okay, so first of all I will present to you two new rules. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. I will repeat again on rule number one. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number one? Actually, if we have a circle and the center of this circle is at this point O, and we have a tangent to this circle this tangent AB is tangent to the circle at this point M, and we have a radius. Actually point M is the point of tangency. Point M is the point where tangent AB is tangent to this circle. Therefore point M is defined as the point of tangency, and if we have a radius of this circle, this is the radius of this circle, OM is the radius of this circle, and the radius OM is drawn to the point of tangency, that is to say to point M. The radius OM is drawn to point M, that is the point of tangency. Therefore, the tangent, according to rule number one, the tangent AB is perpendicular to this radius. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So whenever a radius of a circle is drawn to the point of tangency of a tangent, then that tangent will be perpendicular to that radius. That is to say, as you can see from the drawing, the radius OM is drawn to the point of tangency. That is to say, OM, the radius OM is drawn to point M, that is the point of tangency. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle also equals to 90 degrees. So, a tangent to a circle, tangent AB, is perpendicular to the radius drawn to its point of tangency. So if the radius is drawn to the point of tangency, like in this drawing, the radius is drawn to the point M, that is the point of tangency. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle equals to 90 degrees. Okay, that is rule number 1. And we also have rule number 2. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. I will repeat on rule number 2 again. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal length. So what is the meaning of rule number 2? The meaning of rule number 2 is that if we have this circle and from an external point, that is to say, this point P is an external point of this circle. Why point P is an external point of this circle? Because point P is not located inside this circle nor on that circle, but it is located outside of this circle. Therefore, point P is defined as external point of this circle. So if from the external point P we will draw two tangents to this circle, that will be the first tangent. We will define the touching point between the first tangent to the circle, to this circle, as point A. So this is the first tangent, and we will draw from point P the second tangent to this circle. We will define the touching point between the second tangent to the circle as point B. So actually, according to rule number 2, if from the external point P we draw two tangents to a circle, then the lengths of those two tangents will be equal to each other. So the length of this first tangent is actually PA, and the length of the second tangent is PB. According to rule number 2, the lengths of those two tangents are equal. That is to say, PA equals to PB. Okay, I will repeat again. If from one external point, two tangents are drawn to a circle, so if from the external point P we draw two tangents to this circle, this is the first tangent and this is the second tangent, then they have equal lengths. The length of the first tangent is PA and the length of the second tangent is PB, and according to rule number 2, the lengths of those two tangents are equal. That is to say, PA is equal to PB. Okay? So that was the second rule. In the next step, we will define the center of the small circle as point P, and we will also define the center of this big circle as point Q. Then we will join together points P and A by a straight line. Actually, we will define the touching point between tangent BC, this tangent to the small circle, as point E. Actually, point E is the point of tangency of tangent BC with this small circle, and we have radius PE that is drawn to the point of tangency, that is to say, it is drawn to point E. Therefore, the tangent BC is perpendicular to this radius according to rule number 1. So here this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay, and we also know that all four angles of a square are right angles. Therefore, angle ABC is a right angle. It equals to 90 degrees. We will define the touching point between tangent AB and this small circle as point M. Then we will join together points P and M by a straight line. Actually, PM is the radius of this small circle, that is to say, it equals to R. Why PM is the radius of this small circle? Because of the fact that line segment PM starts from the center of the small circle, that is to say, of this small circle, that is to say, it starts from point P and ends at point M, that is the point on the small circle itself. Therefore, PM is the radius of this small circle, that is to say, it equals to R. And again, we have this radius, the radius PM is drawn to the point of tangency, that is to say, it is drawn to point M. Therefore, according to rule number 1, the tangent AB is perpendicular to this radius PM. That is to say, this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle, it equals to 90 degrees. So we will focus on quadrilateral PEMB. Okay, we will focus on quadrilateral PEMB, this small quadrilateral. Actually, in quadrilateral PEMB, we have 4 right angles. Inside quadrilateral PEMB, we have 3 right angles. 1, 2, 3. And the sum of 3 right angles is 90 times 3 equals to 270 degrees. We will define the fourth angle, angle EPM. This angle is angle Z. And we have a rule that states that the sum of the angles in any quadrilateral equals to 360 degrees. And especially the sum of the angles of quadrilateral PEMB must be equal to 360 degrees. That is to say, the sum of its 3 angles, that is 270 degrees, plus the size of the fourth angle must be equal to 360 degrees according to the rule that I mentioned. Here we will subtract 270 degrees from this equality, and we will get that angle Z equals to 360 degrees minus 270 degrees equals to 90 degrees. So we found out that angle Z is a right angle, it equals to 90 degrees. So we write here that angle Z equals to 90 degrees. It is a right angle. So actually, as you can see from the drawing, quadrilateral PEMB has 4 right angles, and therefore quadrilateral PEMB must be at least a rectangle. I will write it down. Quadrilateral PEMB must be at least a rectangle. If not a square, it must be at least a rectangle. Okay, quadrilateral PEMB must be at least a rectangle, and we have a rule that states that the opposite sides of a rectangle are equal to each other. Opposite sides of a rectangle are equal to each other. That is to say, PE equals to MB. According to the rule that I mentioned, PE equals to MB. Those are two opposite sides of rectangle PE and B, therefore PE equals to MB. But we know that PE equals to R. PE is the radius of this small circle. Okay? So from this equality we will get that MB also equals to R. Okay, MB also equals to R. Likewise, according to the rule that opposite sides of a rectangle are equal to each other, inside the opposite sides of rectangle PE and B, those two sides PM will be equal to EB. PM will be equal to EB. Okay, but we know that PM equals to R. PM is the radius of this small circle. So from this equality we will conclude that BE also equals to R, or EB equals to R. EB equals to R. So actually we found out that all sides of quadrilateral PEMB are equal to each other. They are all equal to the radius of this small circle. Therefore, quadrilateral PEMB is a square. Okay? And if the opposite sides of a rectangle are equal to each other, let alone that the opposite sides of a square are equal to each other. Okay, RPM equals to EB, as you can see, and MB also equals to PE in square PEMB. Okay, so in the next step we will calculate the size of line segment AM. Okay, first of all, it is given us in the question that AB equals to 8 units, so we can go here, AB equals to 8 units. And as you can see from the drawing, MB equals to R. So what is the size of AM? Very simple. AM, this line segment, equals to AB minus MB. AB minus MB is exactly AM. So AM equals to AB minus MB. Okay, line segment AM equals to AB minus MB. AB minus MB equals to AM. Very simple. But we know that AB equals to 8 units and MB equals to R. So in total we got that AM equals to AB, that is 8 units, minus MB, that is R, or AM equals to 8 minus R. AM equals to 8 minus R. So we write here that AM equals to 8 minus R. Okay. The touching point between tangent DA and this big circle will define it. The touching point between tangent DA and this big circle as point O. And as you can see from the drawing, the radius of this big circle, that is actually 2R, is drawn to the point of tangency. That is to say, it is drawn to point O, that is the point of tangency of tangent DA with this big circle. Therefore, according to rule number 1, the tangent DA is perpendicular to this radius. That is to say, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule number 1, that states that a tangent to a circle is perpendicular to the radius that is drawn to the point of tangency. This radius QO is drawn to the point of tangency, that is to say point O. Therefore, the tangent DA is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle is also equal to 90 degrees. And we also know that all 4 angles of a square ABCD are right angles. All the angles of square ABCD of any square are right angles. Therefore, angle ADB or ADC, this angle is a right angle, it equals to 90 degrees. Okay, and we will define the touching point between tangent DC and this big circle as point S. Then we will join together points Q and S by a straight line. Actually, line segment QS is the radius of this big circle, that is to say it equals to 2r. Point S is the point of tangency of tangent DC with this big circle. And we actually have, as you can see from the drawing, this radius QS is drawn to the point of tangency. It is drawn to point S. Therefore, the tangent DC will be perpendicular to this radius. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. So we will repeat on the same process as we did in quadrilateral PEMB. We will do exactly the same process in quadrilateral DSOQ. Okay, so we will focus on quadrilateral DSOQ, this quadrilateral. In quadrilateral DSOQ, we have three right angles, 1, 2, 3. And the sum of three right angles is 270 degrees. And if we define the fourth angle, this angle as angle Z, we have the rule that says that the sum of the angles in any quadrilateral equals to 360 degrees. Therefore, the sum of three angles of quadrilateral DSOQ that equals to 270 degrees plus the size of the fourth angle must be equal to 360 degrees, according to the rule that I mentioned, that the sum of the angles in any quadrilateral equals to 360 degrees. We will subtract 270 degrees from this equality and we will get that angle Z equals to 90 degrees. Angle Z equals to 360 degrees minus 270 degrees. It equals to, that is to say, it equals to 90 degrees. So angle Z is a right angle. It equals to 90 degrees. So we write here that angle Z equals to 90 degrees. So as you can see from the drawing, quadrilateral DSOQ has four right angles, and any quadrilateral that has four right angles must be at least a rectangle. So quadrilateral DSOQ must be at least a rectangle. I will repeat again. Quadrilateral DSOQ must be at least a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, OQ equals to DS, or DS equals to OQ. But we know that OQ equals to 2R. It is the radius of this big circle. Okay, OQ equals to 2R. From this equality we will conclude that DS also equals to 2R. TS equals to 2R. Likewise, the two opposite sides DO and SQ in quadrilateral DSOQ are equal to each other according to the rule that I mentioned, that the opposite sides of a quadrilateral equal to each other. Therefore, we write that DO equals to SQ. DO equals to SQ, but we know that SQ equals to 2R. It is the radius of this big circle. So from this equality, we will conclude that DO also equals to 2R. DO also equals to 2R. So we actually found out that quadrilateral DSOQ has four sides that are equal to each other. Therefore, quadrilateral DSOQ is a square. And I repeat again, if the opposite sides of a rectangle are equal to each other, let alone that the opposite sides of a square are equal to each other. Okay? DO equals to SQ and OQ equals to DS. Okay? In the next step, we will calculate the size of line segment OA. So what is the size of line segment OA? DA is one side of square ABCD, therefore it equals to 8 units. DA equals to 8 units. And DO equals to 2R. So actually, what is the size of line segment OA? OA equals to DA minus DO. OA equals to DA minus DO. Okay? OA equals to DA minus DO. Okay? OA equals to DA minus DO. DA equals to 8 units and DO equals to 2R. So in total we got that OA equals to 8 minus 2R. OA equals to DA that is 8 units minus DO that is 2R. So we found out that OA equals to 8 minus 2R. Okay? So in the next step, we will connect together points Q and A by a straight line. We will define this point as point F, and we will define the touching point between tangent AF and this big circle as point G. We will join together points Q and G by a straight line. QG is the radius of this big circle because of the fact that line segment QG starts from point Q, that is the center of this big circle, and ends at point G, that is a point on the big circle itself. Therefore QG is the radius of this big circle, that is to say it equals to 2r, and again we have the radius QG that is drawn to the point of tangency, that is to say it is drawn to point G, that is the point of tangency of tangent AF with this big circle. Therefore, according to rule number 1, whenever you have a radius that is drawn to the point of tangency of a tangent, then that tangent will be perpendicular to that radius. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And we will define the touching point between tangent AF and this small circle as point H. Then we will join together points P and H by a straight line. Actually, PH is the radius of this small circle because of the fact that line segment PH starts from the center of this small circle, that is to say starts from point P and ends at point H, that is a point on this small circle itself. Therefore PH is the radius of this small circle, that is to say it equals to R. And again we have this radius PH that is drawn to the point of tangency, that is to say to point H. That is therefore, according to rule number 1, whenever you have a radius that is drawn to the point of tangency of a tangent, then that tangent will be perpendicular to this radius. That is to say, this angle equals to 90 degrees, it is a right angle, and this angle also equals to 90 degrees. Okay? Whenever you have a radius that is drawn to the point of tangency of a tangent, then the tangent will be perpendicular to that radius. That is to say, this angle is 90 degrees, and this angle also equals to 90 degrees. Okay? So, in the next step, we will prove that those two right triangles can go into each other. Actually, we will prove that the right triangle, triangle APM, is congruent to the right triangle, triangle APH, this right triangle. I repeat again, we will prove that the right triangle APM is congruent to the right triangle APH. Okay, those two right triangles can go into each other. First of all, we know that side AM of triangle APM equals to side A edge of triangle APH, according to rule number 2. AM equals to AH according to rule number 2. So repeat on rule number 2. We have here external point of this small circle. Point A is external point of this small circle, and from point A we have two tangents to this small circle, tangent AM and tangent AH. According to rule number 2, whenever you draw two tangents from an external point of a circle to that circle, then the length of those two tangents will be equal to each other. The length of this first tangent is AM, and the length of this second tangent is AH. And according to rule number 2, the length of those two tangents are equal to each other. That is to say, AM equals to AH. Okay, and we also know that PM equals to PH equals to the radius of this small circle. PM equals to PH equals to the radius of the small circle. And here we have also a common side, PA. This side PA is a common side. It belongs to both triangles. PA equals to PA is a common side that belongs to both triangles. I will repeat again. PA equals to PA is a common side that belongs to both triangles. So we actually proved that all three sides 1, 2, 3 of the right triangle APM are correspondingly equal to the three sides of triangle APH 1, 2, 3. Therefore, we actually proved that triangle APM is congruent to triangle APH according to side rule. I will write it down. We proved that the right triangle APM, congruent. This is the sign of congruent. So the right triangle APM is congruent to the right triangle APH. According to side rule. So what is actually side rule? Side rule is that if you prove that all three sides of one triangle are correspondingly equal to all three sides of the other triangle, then you actually prove that those two triangles can go into each other according to side rule. Okay? So from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other. Therefore, the two corresponding angles, those two corresponding angles will be equal to each other. That is to say, angle PAM, this angle will be equal to angle PAH, this angle. Angle PAM equals to angle PAH according to the rule that corresponding angles in congruent triangles are equal to each other. And if we define angle PAM as alpha, then angle PAH will be also equal to alpha. because of the fact that those two angles are equal to each other. So we actually found out that angle PAM equals to angle PAH equals to alpha according to our definition. So in the next step we prove that those two right triangles can go into each other. Okay, exactly the same way actually, according to side rule. So we'll focus on this right triangle, triangle AQG. And the right triangle, triangle AQO. This right triangle. I'll repeat again. We'll prove that the right triangle AQG is congruent to the right triangle AQO. Okay. Actually, we know that side AG of the right triangle AQG is equal to side AO, this side of the right triangle AOQ, according to rule number 2. AG equals to AO according to rule number 2. I'll repeat again on rule number 2. From point A, the external point of this big circle is point A, and from point A we have two tangents to this big circle. We have tangent AG, and the second tangent is tangent AO to this big circle. And according to rule number 2, whenever you have two tangents from an external point to a circle, then the lengths of those two tangents are equal to each other. The length of this first tangent is AG, and the length of this second tangent is equal to AO. That is to say, AG equals to AO according to rule number 2. Okay, and we also know that QG equals to QO equals to the radius of this big circle equals to 2R. QG equals to QO equals to the radius of this big circle, that is actually 2R. QG equals to QO equals to 2R. That is the radius of this big circle. And we have also a common side. QA is a common side, it belongs to both triangles, so QA equals to QA is a common side that belongs to both triangles. Again, QA equals to QA is a common side that belongs to both right triangles. Again, we actually proved that three sides of the right triangle AQG are corresponding equal to three sides of the right triangle AQO. Therefore, those two right triangles can go into each other according to side rule. So I'll write it down. I actually proved that the right triangle AQG is congruent to the right triangle AQO. I will remind you again that this sign is sign of congruent. So the right triangle AQG can go into the right triangle AQO according to side rule. And from the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can point to each other, therefore the two corresponding angles, those two corresponding angles will be equal to each other. So I write it down, angle QAG is equal to angle QAO angle QAG equals to angle QAO, and if this angle equals to beta, then this angle will be also equal to beta because of the fact that those two angles are equal to each other. So we actually found out that angle QAG is equal to angle QAO, and it is equal to beta according to our definition. Okay? We actually know that angle DAB, this angle, is one angle out of four angles of square ABCD. And we know that all the angles of a square are right angles, therefore angle DAB equals to 90 degrees because it is one of out of four angles of square ABCD, therefore it equals to 90 degrees. That is from one side, but from the other side, the size of angle DAB is the sum of the four angles that it consists. Angle DAB consists of four angles, alpha, alpha, beta, and beta. And the sum of those four angles equals to angle DAB. That is to say, 2 alpha plus 2 beta equals to angle DAB. So we have here that angle DAB equals to 90 degrees from one side, but from the other side it equals to the sum of the four angles that it consists. Okay, so from this equality we will conclude that 2 alpha plus 2 beta equals to 90 degrees. This will be equation number 1. Here we will divide the equation number 1 by 2, and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. But if alpha plus beta equals to 45 degrees, then tangents alpha plus beta will be equal to tangents 45 degrees. Very, very simple. Tangents alpha plus beta will be equal to tangents 45 degrees. And we know that tangents 45 degrees equals to 1. So we have equation number 1 that says that tangents alpha plus beta equals to 1. Actually, we have trigonometric identity for the value of tangents alpha plus beta. According to the following trigonometric identity, the value of tangents alpha plus beta is tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta. Okay, so the trigonometric identity is that tangents alpha plus beta equals to tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta. So here we will substitute tangents alpha plus beta in equation number 1, this equation, by this expression that equals to tangents alpha plus beta according to this trigonometric identity. So we will do it now. So instead of tangent alpha plus beta in equation number 1, this equation, we write down this expression that equals to tangent alpha plus beta. So equation number 1 will be tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. And according to equation number 1, tangent alpha plus beta equals to 1. So we got this expression after we substituted tangent alpha plus beta by this expression that equals to tangent alpha plus beta according to this trigonometric identity. So in the next step, we'll find out the values of tangent alpha and tangent beta. We'll find out the values of tangent alpha and tangent beta, and we will substitute tangent alpha and tangent beta in this equation number 1 by the values that we will find out for tangent alpha and tangent beta. And we will find out the values of tangent alpha and tangent beta from this drawing. If we focus on the right triangle, triangle APM, so in the right triangle, triangle APM, this right triangle, tangent alpha equals to PM over AM. I will repeat again. In the right triangle, triangle APM, tangent alpha equals to PM over AM. But what is the value of PM? PM equals to R, the radius of the small circle, and AM, we have already found out that AM equals to 8 minus R. 8 minus R, so actually we found out that tangent alpha equals to R over 8 minus R. Tangent alpha equals to R over 8 minus R. In the next step, we will focus on the right triangle, triangle AQO. So in the right triangle, triangle AQO, tangent beta, here tangent beta equals to QO over AO. I'll repeat again. In the right triangle, triangle AQO, tangent beta equals to QO over AO. But what is the value of QO? QO equals to R. From the drawing we can see that QO equals to 2R. And AO, we have already found out that AO equals to 8 minus 2R. So in total we found out that tangent beta equals to 2R over 8 minus 2R. Okay, and we have already found out that tangent alpha equals to R over 8 minus R. Okay, so we will substitute, as I already said, we will substitute the values of tangent alpha and tangent beta in this equation number 1 by those two values that we found for tangent alpha and tangent beta. Okay, so we will do it now. So equation number 1 will be, instead of tangent alpha, we will write down this expression that equals to tangent alpha, R over 8 minus R plus tangent beta, and instead of tangent beta, we will write down this expression 2r over 8 minus 2r that equals 2 times beta. Here it is over 1 minus tangent alpha times tangent beta. So tangent alpha equals to r over 8 minus r, and tangent beta equals to 2r over 8 minus 2r. And all this expression equals to 1. So we substituted tangent alpha and tangent beta in this equation number 1 by those two values for tangent alpha and tangent beta, and we got this expression. So here we'll take out a common factor for those two expressions, and we will also take a common factor for 1 and this expression. So the common factor in the numerator will be 8 minus r times 8 minus 2r, and we must multiply r by 8 minus 2r in order to get this expression, and here we will multiply 2r by 8 minus r in order to get this expression, and all divided by 1 minus this expression. We will substitute 1 by 8 minus r over 8 minus r, that actually equals to 1, and then we will multiply it by 8 minus 2r over 8 minus 2r, that is also equals to 1. So here we have actually 1 times 1 is still 1. So all this expression equals to 1, and then we'll subtract from this expression from 1, this expression in the numerator we have r minus r times 2r is minus 2r squared. Okay, so here we have 8 minus r times 8 minus 2r in the numerator, and we have 8 minus r times 8 minus 2r, exactly the same expression in the denominator, so they will be cancelled by each other, because when we divide one by the other, it will be 1, that is to say it will get cancelled. So those two expressions will get cancelled, and what is left after, and all actually equals to 1, of course. This expression equals to 1. So what is left after we cancel those two expressions? What is left is actually r times 8 minus 2r plus 2r times 8 minus r, all divided by 8 minus r times 8 minus 2r minus 2r squared, all equals to 1. Okay, so here we'll cross multiply this expression, and we will get that r times 8 minus r times 8 minus 2r plus 2r times 8 minus r, it equals to 8 minus r times 8 minus 2r minus 2r squared. So actually after we cross multiplied this expression number 1, we got this expression. Here we will open the brackets in both sides of equation number 1, and we will get that r times 8 is 8r, r times minus 2r is minus 2r squared, 2r times 8 is 16r, 2r times minus r is minus 2r squared, all equals to 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, minus r times minus 2r is plus 2r squared, minus 2r squared, actually plus 2r squared minus 2r squared equals to 0, so those two expressions will get cancelled. So what is left after we cancelled those two expressions? Here we have 8r plus 16r is 24r, minus 2r squared is minus 4r squared, all equals to 64 minus 16r. Minus 16r minus 8r is minus 24r. Here we will subtract 24r from equation number 1, and we will get that minus 4r squared equals to 64 minus 24r. Minus 24r is minus 48r. We will add 4r squared to this quadratic equation, and we will get that 4r squared minus 48r plus 64 equals to 0. We divide this quadratic equation by 4, and we will get that r squared minus 12r plus 16 equals to 0. So we have this quadratic equation that r squared minus 12r plus 16 equals to 0. Actually, the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following equation, that x equals to minus b plus minus root of b squared minus 4 times a times c over 2a. Here a, b, and c are also the coefficients of this quadratic equation, and x is the variable that we are looking for. And in our specific quadratic equation, the variable is r, so actually x equals to r. The coefficients a, b, and c are as follows: A equals to 1, B equals to minus 12, and C equals to 16. So we will put this data inside this equation in order to find out the value of R. X equals to R, so it is R equals to minus B. B equals to minus 12, so minus B is minus 12, that is actually 12, plus minus root of B squared. B equals to minus 12, so minus B squared is minus 12 squared, that is 144, minus 4 times A is 1, so minus 4 times 1 is minus 4, minus 4 times C is 16, so minus 4 times 16 is minus 64, over 2 times A. A is 1, so 2 times 1 is 2, and here we have so the radius equals to R equals to 12 plus minus 144 minus 64 is 80 over 2. R equals to 12 plus minus 80 is 4 times 20, so I will write it down. 4 times 20 over 2. The root of 4 is 2. And inside the root we have only 20 over 2. So the radius R equals to 12 over 2 is 6, and 2 over 2 is 1, and 20 is 4 times 5, so I'll write it down. The root of 4 is 2, so we will get that the radius R equals to 6 plus minus the root of 4 is 2, and inside the root we have only 5. So we got two solutions for R, or two roots for R. The first one is that R equals to 6 plus 2 times root 5, and the second solution for the quadratic equation is that R equals to 6 minus 2 times root 5. Okay? So here as you can see from the drawing, the one side of a square equals to 8 units. AB equals to 8 units, and the small circle is totally located inside this square. Therefore, the radius of this small circle must be less than 8 units, because of the fact that the small circle is totally located inside the square. Therefore, the radius of this small circle must be less than 8 units. Otherwise, it will not be located totally inside this square. But as a matter of fact, we know, as you can see from the drawing, the small circle is totally located inside this square. Therefore, the radius must be less than 8 units. Okay, so R must be less than 8 units in order that the radius, in order that the circle will be located totally inside, and the square, the radius must be less than 8 units. But here R equals to 6 plus 2 times root 5 units is bigger than 8 units. So this answer that the radius of the circle is greater than 8 units is incorrect answer, because of the fact that the radius is totally located, the circle is totally located inside this square. Okay, and we left only with the answer that the radius of the small circle equals to 6 minus 2 times root 5 units, or in terms of numbers, the radius of the small circle equals to 1.53 units. Okay, so I repeat again on the answer. We found out that the radius of this small circle R equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the radius of this small circle, or the size of R, or the value of R. We have here a square ABCD. One side of square ABCD equals to 8 units. And the radius of this big circle equals to 2R, while the radius of this small circle equals to R. And we want to find out the value of R, or the size of the radius of this small circle. Okay, so in order to find out the radius of this small circle, I presented to you two new rules. The first rule was that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. I'll read again. A tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if you have this circle and the center of this circle is at this point O, and we have tangent AB to this circle. Tangent AB is tangent to this circle at point M, that is to say point M is the point of tangency of tangent AB with this circle. So if we have a radius that is drawn to the point of tangency, that is to say to point M, like in this drawing, then the tangent AB will be perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. So whenever we have a radius that is drawn to the point of tangency of that tangent, then the tangent will be perpendicular to that radius. In our drawing, this radius OM is drawn to the point of tangency, that is to say to point M. Therefore, the tangent AB is perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, so that is rule number 1. And we also have rule number 2. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. I read again, if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? The meaning of rule number 2 is that if you have external point to a circle, point P is an external point of this circle. Why? Because point P is not located inside this circle nor on that circle, on this circle, therefore but it is located outside of this circle, therefore point P is defined as external point of this circle. And if from the external point P you draw two tangents to this circle, then the lengths of those two tangents will be equal to each other. The length of this first tangent is PA and the length of the second tangent is PB. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say PA equals to PB. Okay, so whenever you draw from an external point of a circle two tangents to that circle, then the lengths of those two tangents will be equal to each other. In our drawing here, from the external point P, we drew two tangents to this circle, therefore the length of those two tangents will be equal to each other. That is to say PA will be equal to PB. Okay? So in the next step, we actually proved that those two right triangles can go into each other according to side rule. Therefore, we concluded that if this angle is alpha, this angle also will be equal to alpha because of the fact that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. And we also proved that those two right triangles can go into each other according to side rule. Therefore, those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be equal to each other. So if this angle is beta, then this angle will be also equal to beta because of the fact that those two angles are equal to each other. Okay? And here we actually proved that rectangle PEMB is a rectangle, and quadrilateral PEMB is at least a rectangle because it has four right angles, and therefore, when we know that the opposite sides of a rectangle are equal to each other, therefore PM equals to EB and PM equals to R, therefore EB also will be equal to R, and also PE equals to MB, and PE equals to R, therefore MB will be also equal to R. And we did the same thing in this quadrilateral. We prove also that this quadrilateral is a square. Okay, therefore all of its sides are equal to each other, all of its sides are equal to 2R, and we know that angle DAB equals to 90 degrees because it is one of the square ABCD angles, and all the angles of a square are right angles, therefore angle DAB of square ABCD equals to 90 degrees. That is from one side, but from the other side, angle DAB consists of 4 angles, therefore angle DAB equals to 2 alpha plus 2 beta, and so for one side angle DAB equals to 90 degrees, but from the other side angle DAB equals to 2 alpha plus 2 beta, and from this equality we concluded that 2 alpha plus 2 beta equals to 90 degrees. We divided the equation number 1 by 2 and we got that alpha plus beta equals to 45 degrees, but if alpha plus beta equals to 45 degrees, then tangens alpha plus beta will be equal to tangens 45 degrees. Tangens 45 degrees is 1, so we got that tangens alpha plus beta equals to 1. And we have trigonometric identity for tangens alpha plus beta, and we substituted tangens alpha plus beta by this expression that equals to tangens alpha plus beta, and we got this equation number 1. Then we substituted tangens alpha and tangens beta by the values that we found out in this drawing for tangens alpha and tangens beta. In this right triangle APM, tangens alpha equals to R over 8 minus R, and in this right triangle AOQ, tangens beta equals to 2R over 8 minus 2R. Okay, so we substituted tangens alpha and tangens beta in this equation by the values that we found. For tangens alpha is R over 8 minus R, and tangens beta, as I've already showed you, it equals to 2R over 8 minus R. Okay, and we got this expression. We solved this equation number 1, and we got 2 solutions. The first solution is that the radius of the small circle equals to 6 plus 2 times root 5 units, but it is impossible that it equals to 6 plus 2 times root 5 units that is greater than 8 units, because of the fact that the small circle is totally located inside the square. So the radius of this small circle must be less than 8 square in order to be totally located inside the square. So this answer is not correct answer, and we left only with the possibility that the radius of the small circle equals to 6 minus 2 times root 5 units, or in terms of numbers, the radius of the small circle equals to 1.53 units. Okay, so the answer to the question is that the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, thank you very much.